and welcome to another WJEC A level physics question. This time is question 2 from June 2015's PH5 paper. It's a question on electromagnetic induction, which nowadays is in Unit 4. What we got in the question is a square loop of size 0.815 meters rotated through 90 degrees in a uniform magnetic field of 65 microteslas. And we've got 3 diagrams showing the same square loop at different times. We've got to determine the magnetic flux through the square loop at t equals 0. Well, hopefully just looking at the diagram you can see that none of the flux is actually passing through the loop, so we could simply write 0 Webers. Or, if we prefer, we could use the formula for magnetic flux, which is BA cos theta. Theta here is the angle between the magnetic field lines and the normal through the face of that coil, and that would be 90 degrees, and cos of 90 is 0, so whichever way we do it we end up with 0 Webers. We've also got to find the magnetic flux at t equals 0.12 seconds, and we can simply use again phi equals BA cos theta. This time the angle between the magnetic field and the normal through the coil is 0 degrees, so cos of 0 is 1. So we can simply use here that phi is equal to B times A. So B is 65 microteslas, and the area will be 0.815 squared. And if we put those numbers into a calculator, we come up with 4.3 times 10 to the minus 5 Webers. The square loop is made of copper, and we've got to explain why there's a current in the loop as it's rotated. Well, Faraday's law tells us that there will be an induced EMF. And that's because the flux through the coil is changing. So there's an induced EMF, also there's a complete circuit. The loop makes a complete circuit itself. And therefore current will flow. For part C, we're going to explain how Lenz's law will give the direction of the forces acting on the sides P, Q and RS as a square loop is rotated. Well, Lenz's law tells us that the direction of the induced EMF will oppose the change of flux. So if we look back at the diagram, this loop is being rotated anti-clockwise here, so the forces on sides P, Q and RS will be such as to try to rotate the loop clockwise to stop it from rotating. Okay, next, the copper wire from which the square loop is made has a circular cross-section of diameter 6 millimeters. We're given a resistivity of copper as 1.67 times 10 to the minus 8 ohm meters. We've got to calculate the mean current flowing through the square loop as it's rotated between t equals 0 and t equals 0.12 seconds. Okay, so we're going to end up using I equals V over R, but to be able to find R, we need to use the resistivity formula, R equals rho L over A. And before we can use that, we need to find the cross-sectional area of the wire. The cross-sectional area of the wire will be pi r squared. The diameter of the wire is 6 millimeters, so the radius is 3 millimeters. So that will give us, one second, a cross-sectional area of 2.8 times 10 to the minus 5 meters squared. Now we can work out the resistance. So R is rho 1.67 times 10 to the minus 8 times the length. Now the length of the wire used to make this copper frame is 0.815 meters per side, and there are 4 sides, divided by that area that we've just calculated. So that will give us a resistance of about 1.9 times 10 to the minus 3 ohms. Now we're still not quite ready to use I equals V over R. We've got to find V, and V is basically the induced EMF, which is calculated from the change of flux linkage per second, or the rate of change of flux linkage. Here N is 1 because it's just a single term of wire. The flux changes from 0 in the first position to 4.3 times 10 to the minus 5 in the second position. So the flux change is 4.3 times 10 to the minus 5, and this happened in 0.12 seconds. That will give us an induced EMF of about 3.6 times 10 to the minus 4 volts. And now finally, the current will be V over R, 3.6 times 10 to the minus 4 over 1.9 times 10 to the minus 3, and that comes out to be 0.19 amps. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.